right. I'm Robin. I'm from Northeastern. And I'm going to talk to you about approximate and unknown symmetry. So like broadly what I'm talking about is I work a lot on equivariant neural networks, which are very effective but use a very strong inductive bias of knowing exactly what the symmetry is in the problem. And I want to talk about how to extend that to slightly weaker inductive biases, that there is some symmetry or something like that we can still take advantage of. Okay. So the type of problems that I think about are problems that involve dynamics and symmetry, which is quite a broad class of problems. And the common strategy that I use to approach those problems is I locate some, I'm not a domain expert in all of the domains that I showed, right? But I locate some kind of mathematical model for the time evolution of that system that I want to study. Then I extract the symmetries of that system. Then I forget the mathematical model. I just keep the symmetries. Then I build a neural network that has those symmetries built into it as constraints. And then I train that model to try to understand the time evolution of that system, for example, like solving a PDE or something like that. So like one of the usefulnesses of this, right, is like in a lot of these domains that I consider, for example, like climate science is a good one. I'm not necessarily talking about fully observed systems or systems where I could actually have an exact differential equation that would be useful for actually numerically simulating the model. And so I think of the neural network as helpful for inferring aspects of the partially observed dynamics, partially observed conditions, or even just sampled data that I'm using to try to infer the rest of the system. That said, right, if I'm thinking about something like ocean fluid dynamics and trying to extrapolate based on like satellite data or reanalysis data of the ocean, I can still expect that a large amount of the dynamics is going to come from the basic fluid dynamics that would apply in a small simulation. So sort of in the program that I outlined, right, if I want to do something like study fluid dynamics, right, I look at the Navier-Stokes equation that would govern these dynamics, right? I extract the symmetries of this system. So here I would have some Galilean invariance together with this anisotropic scaling law. Okay, and then I forget the Navier-Stokes equation. I just take the scaling law. Okay, so this is some spatial and temporal and magnitude scaling law. And then I try to build a neural network that incorporates this scaling law directly. So the like poster child for equivariance in neural networks is convolutional neural networks. So all sorts of equivariant neural networks always involve some sort of weight sharing or weight tying. I'm applying the same weights across the different values of that symmetry group. And that's what gives me the equivariance or the symmetry in the output. So here, for example, right, is the standard like two-dimensional convolutional neural network. And here I'm taking the same kernel values, k of q, and I'm applying them across the entire image. And that's how I attain translation equivariance in the network. So like hopefully you can roughly see, right, if I want to build a scale equivariant neural network for directly incorporating the scaling law from Navier-Stokes equations into my neural network for simulating some fluid dynamics, right, I can take the same kind of principle where I take the same value of the kernel, the same weights, and I apply them across the input values at different scales, and I use specifically the scaling law that applies to the fluid mechanics. Okay, so like in this case, right, what we're interested in is most of the papers that you see like in machine learning conferences that are approaching problems like fluid mechanics. If you recreate a lot of the results, right, what you'll see is that a lot of these models are fairly overfit to the specific parameters of the system that they study. So it is a small data regime. It's very expensive to collect this data, even by simulator. And so what you end up with is, without any sort of like strategy to mitigate the overfitting, you end up with a model that's fairly specifically fit. And when you try to change something, for example, the scale of the fluid, the model rapidly accumulates error, right? So here, what this result shows, right, is that when we incorporate this equivariance into the model, then we're able to have a model that can generalize across scale. Yeah.
So what does the network do?
Sorry?
What does the network do? What is
Oh, so in this case, the task is just the forward prediction of the velocity field for the fluid. So it's just applied autoregressively. We take in past samples of the velocity or the velocity and density, and we predict the future of them, right? And so, like, for example, like here what this graph is showing, right, is that if you take a non-equivariant model and you change the scale of the fluid, the error shoots up, right? If you take our equivariant model, it's able to generalize across scale. Okay. Okay, so that was sort of like, that's the equivariant path, okay? And now I want to talk about what happens when I look at real-world data that isn't perfectly equivariant, right? So for example, like one of the symmetries of the Navier-Stokes equations, if I emit any kind of external forcing, would be rotational symmetry, right? So the advection diffusion is going to be rotationally symmetric, right? But all sort of like real-world fluid data that I might study is going to have some kind of symmetry breaking parameters, right? Some kind of external forcings or boundary conditions that are going to break symmetry. Okay. Nonetheless, in a lot of regimes, right, the symmetric terms are still dominant parts of the mechanics, right? And so what I want is I'd like to have a model that can accommodate some amount of symmetry breaking while still leveraging the advantage of understanding that most of the dynamics are symmetric. Okay, so what this plot shows, which I'll show like the actual experimental version of this plot in a second, right? Which is if I apply, so what this plot is along the x-axis, I'm showing an increasing amount of equivariance error or symmetry breaking in the data in the model domain. Okay? In the y-axis, I'm showing the amount of symmetry that I'm forcing my model to have. Or I can measure the amount of symmetry that a trained model has, or an untrained model class. Okay? And what we see is if you take a model just like that has no symmetry bias, for example, like a fully connected model, and I train it, it doesn't really ever learn very much equivariance, very much symmetry, at least in our empirical result. There is some slight slope to this line, so it does learn some, but it doesn't learn zero. It doesn't learn as well as a constrained model, which is not surprising to you if you study constrained models, right? At the same time, the perfectly equivariant model is forced to always be equivariant, can't adapt if the data shows that it is not symmetric, right? So this green line is our goal, right? This line with slope 1, where the model has exactly the amount of equivariance error that the data also shows. Okay, so here's our method, right? So on the left is the group convolution operation. This is the model that shares weights. So you can see that this operation is equivariant because the kernel phi only depends on the multiplicative difference G inverse of H, right? A full linear map could have a different weight for each value of H and G. Okay, so what we do is we insert this weight, WL, that depends only on H into the kernel. And there's this index L, which is the number of kernels phi L. So by modulating how many kernels phi L, each of which is equivariant on its own, and adding these symmetry breaking parameters WL, which are trainable, right, we allow the model to deviate from a perfectly equivariant solution and learn an increasingly non-equivariant solution depending on how many additional kernels we add, right? If you add enough kernels, then in theory you now have a model that could can be completely unconstrained. Okay, and then we also build a similar version for steerable convolution. Okay, so here's the results. So here we did some simulated fluids where we're varying some gravitational force that can start off being very weak and become very strong. Okay, and we compare to both fully equivariant methods, completely unconstrained methods, methods that have, it's hard to, in this case, our unconstrained method is still a convnet, so it still has translation equivariance, but in this case, it wouldn't have rotational equivariance, which is what we're testing here, since it would sort of, at this point, we sort of know that convnets work so well because of the image inputs that it would be hard to say that's a fair comparison otherwise. But here's the empirical version of the chart that I showed earlier. Okay, so along the x-axis, we're increasing the the external force that's breaking symmetry. Along the y-axis, we're empirically testing how much equivariance error our learned model has. If you look at the blue line, right, this is the perfectly equivariant network, and it is sticking to its guns of having zero equivariance error. Things must be completely symmetric. That dotted line would be the optimal solution. Our method is the green line, which you notice is able to smoothly interpolate. It really stays perfectly symmetric if the data tells it to. But as the data becomes less symmetric, the model will adapt. So that's the goal. It's kind of interesting. I guess you look at RPP, residual pathway prior, is another approximately equivariant method where they simply add, for example, like for translation equivariance, it would be a fully connected layer plus a convolutional layer. So, and they place a bias towards the convolutional layer, but it doesn't adapt as well here. Okay, so this is sort of the approximate or relaxed equivariant network. So then I'll take one step further. So suppose I want to impose I want to propose the very, very weak inductive bias that I believe the data has some symmetry, but I don't know a priori what it is. Okay? So essentially what we're doing here is we are training something based on an equivariant neural network. So it's something like a group convolution, although here we're linearizing and we're using a Lie algebra action in a small space. And we're essentially learning the generators of that Lie algebra. So we're trying to learn the infinitesimal symmetries of the data set. And the way those are learned is it's just trained end to end. So it's an equivariant neural network where the equivariance is learned as you go, right? And so those generators, those symmetries are going to be whatever symmetries, whatever correlations the model finds in the data that aid learning, okay? And it's kind of neat. So like in this picture, for example, right, this would be the example of the generator of symmetry that we learn. I think this is either a small shift. I think it's a small rotation to a flattened image. That's why it has that repeating pattern. And then this would be the exact numerical solution. Okay, so that's.
Perfect. I would suggest that we go to both speakers to the whole session of questions and answers. And so maybe you want to come in up here, or I don't know how you want to do it. Yeah, we'll start, but I'm just saying, you can ask questions both of the speakers.
I have two questions. First,
do you mind reminding me your name?
Oh, I'm Chaim Stampolinsky. I'm theoretical neuroscientist and physicist. So one question is about the whole goal of discovering or incorporating approximate symmetries. For this particular computation of computing the velocities, it's obvious to expect that this will be a good step. But for other purposes, for instance, if I have a problem of image classification, object classification, or scene reasoning, or whatever, where there is obvious symmetries, but is it clear that this is a good inductive bias to improve on performances?
Yeah, that's a good question. So equivariant neural networks have done really well on various image computer vision benchmarks.
I understand, but the question is whether to actually incorporate approximate symmetries whether the network really has to learn. Okay, convolution captures, but going beyond just saying, okay, so convolution is a good inductive bias, whether you tested your methods in some downstream computation.
Or whether we did.
Yeah. But beyond reproducing the dynamics that obviously has symmetries in it.
Yeah, I mean, I don't think I have like a task here that goes beyond just sort of forecasting various dynamic systems. I mean, we have done quite a few. We applied this to the ocean currents, like I said. We did a bunch of different turbulence data sets. We did trajectory predictions. And we also did various dynamics in some robotics environments.
And just the second question is, in the discovering symmetry,
yeah.
Did you discover a surprising symmetry that?
That's a great question. Discovering symmetry, I would say, is at an early stage. And one of the things, so like earlier in this conference, people were talking about like identifying the system, right, or possibly producing like outputs that could help us like scientifically interpret what we're studying. The outputs that we attain here, I would say, to me, lack interpretability. So like in this visualization, because I knew what the exact symmetry was, I could look at what the Lie algebra generator was and compare it and identify it. But in general, what we get for various data, especially data where I don't know the symmetries, is just various sort of like correlations in the input features that are hard to interpret. I can load them back into the model and see what transformation they correspond to by applying them to the data and exponentiating them, but even then it can be hard to understand. So I would say that interpretability is sort of the next step there. That said, what differentiates our work from other work is that we're working in the full space. So like, by which I mean like our prior on the space of potential symmetries is GL R to the dimension of the input. So compared to like other works like Augurino, for example, where their prior is just like spatial symmetries. So like, for example, for us, right, it would be R to the 32 squared if you have an R, then GL of that, right? Whereas they would have a 6-dimensional affine translation, rotation, shear, right? So it's sort of a trade-off there, right? We can capture more symmetries, but they're less interpretable.
Robin, thanks for the talk. You're going to make my life a lot easier tomorrow since you've already primed everyone for equivariance. So I think at a core level, I think we like agree on a lot of like the things you presented. But I'm gonna frame it in a slightly different way, and I'm curious if you think that is a still like faithful kind of representation of kind of the things you're pointing out. So the reason to impose equivariance is not necessarily because your data is symmetric, it's because your representation of your data has a symmetry. So in this case, that there's your choice of coordinate system is fundamentally arbitrary. But in your case with this jet, this actually isn't the case because the jet is coming in from a particular, there's like an experimental setup. So in a way, it's you have missing data. So in this situation, like this forcing function is not being given to the model, and you want to learn that. And so if the model only has scalar parameters, it will never be able to learn something that's symmetry breaking because you've constrained it to only have scalar parameters. So in a way, the way that you can either parameterize it in like the convolutions, or you could pass it actually to the input. You could actually have like a second input that has non-scalar properties that you could have pushed this through. And it's interesting to see you putting it into the model versus in the input. But I think the thing is basically how do you have the model learn symmetry breaking information?
Right, yeah, I think that's a reasonable perspective. I will clarify something about this like jet experiment. So the full data set here actually includes jets from different directions, right? It's that the dynamics are altered based on the direction.
I see, so it should pick up, basically infer, say, oh, okay, looks like there's a jet coming from this way, and this is gonna alter the dynamics later on.
That's the idea, yeah.
Got it, cool.
Essentially, the force of the jet varies a little with the direction, right? So this breaks the symmetry of the system.
Cool, interesting. And then when you look at the kind of the bias that it's learning, do you see a particular subgroup that corresponds to the subgroup of your data?
Yeah, it's a good question. I don't think we really looked at it that way.
Okay, yeah. Anyway, thanks.